Okay, look at this problem. It is like, fourth order differential equation, right? So this one, like we cannot solve this problem with the previous method. Well, actually we can do it because like your characteristic equation will be r to the 4 minus 1, and you're gonna have like two real number and two imaginary number, which means your solution will be e to the t and e to the minus t and sine and cosine combination form, okay? But you can do that, okay? But like, for here, since like we are talking about Laplace transform, let me show you how we can do, how we can use Laplace transform, okay? Then this is Laplace transform of the fourth derivative of y minus y. It will be just like y of s equals 0, right? And by the lifting, okay? And we already talked about like the lifting of this one, right? It is s to the fourth ys and minus s cubed y0 minus s squared y prime 0 and minus s y double prime 0, and the very last one is minus y triple prime of 0. Okay, now let me plug in everything. Then this will be written by s to the fourth ys minus s cubed, and y0 is given here, right? 0, and y prime 0 is given by 1, and y double prime 0, and y triple prime is also 0. And we have like this one, right? Which is y of s equals 0. We're almost there, okay? So let me gather all the ys term as we did before, s to the 4, and what else? I'm talking about this guy and this guy, right? Minus 1, that's it, equal to, this is 0, and this is s minus s squared, which is s squared on the right hand side, and that's it, right? And divide by s to the 4 minus 1 on both sides, then y s equal to s squared over s to the 4 minus 1. Okay, unfortunately we don't have like this form on the table, but if you write this one as like that, then it is easy, right? So we're going to do the like partial fraction again, a over s squared plus 1 plus b over s squared minus 1. Then like I believe you are better than me like to use the partial fraction. Then you can easily find constant a and b for each term. Then let me skip that part. It is 1/2 over plus 1 plus 1/2 over s squared minus, which can be written by 1/2 times 1 over s squared plus 1 plus 1/2 of times 1 over s squared minus, you understand what I'm saying, right? Like the reason why we have to write like this way is like whenever you have to check the Laplace transform table, and you can easily find this is number 5 and this guy is number 7, which is hypersine, right? There we go. Okay, we're almost here. Then now my solution curve, which is inverse Laplace transform of ys is equal to 1/2 an inverse Laplace transform of 1 over s squared plus 1 plus 1/2 inverse Laplace transform of 1 over s squared minus 1. Okay, then when you compare the table, it is just sine t, but the second one is hypersine of t. Okay, but like when you compare, like as I talked about it, your solution must be like e to the something, right? But like it is easy because like we know about the definitions. Hypersine is equal to e to the t minus e to the minus t over 2, which is equal to, let me say it is, or 1/2 sine t plus 1/4 of e to the t minus t. But you know what? Either way, okay, you can answer by this hypersine form, or you can write like this way. But I just want to show you like the answer from the Laplace transform is equal to the like answer from the characteristic equation. Okay, thank you.